In previous units, we've talked about acids and bases, but it's time to take a little bit of a deeper dive into them. So far, we've mostly familiarized ourselves with the idea of an Arrhenius acid or an Arrhenius base. An Arrhenius acid is just a substance that releases these H plus ions, these hydrogen ions, whenever you dissolve them in water. Now, it's important to understand what a hydrogen atom is. A hydrogen atom is just one proton and one electron. So if you lose that one electron and become positively charged, you become an H plus ion, all that's left is a proton. So Arrhenius acids release these protons when they're dissolved, and Arrhenius bases are just substances that release hydroxide ions, OH minus, when they're dissolved. Those definitions are okay, but it's far better to think throughout this unit in terms of Bronsted-Lowry acid and bases instead. And a Bronsted-Lowry acid is simply something that donates that hydrogen ion or donates that proton. And the Bronsted-Lowry base is what accepts that proton. You can't have a Bronsted-Lowry acid without there being a Bronsted-Lowry base, because if something is going to donate the proton, something has to be there to accept that proton. So let's look at two equations. Here we have an equation up top in red. We have HNO3 reacting with water to make an ion here and another ion here. We'll address those ions in a moment. But if you look, you can see that this HNO3 here wound up releasing one of its, or I guess its only hydrogen, to become an NO3 1- ion, to become a nitrate ion. Since this HNO3 here donated its H, that is considered to be the acid. It donated the H over to something else. The water then must be our base, since you can't have an acid without a base. But let's just check to make sure. The H2O became this weird H3O plus ion. Well, that in fact did accept that hydrogen ion, so it is in fact acting as the base. Now, whatever the base becomes is called the conjugate acid. Conjugate acid. And the reason for that is because now that it's gained that extra hydrogen, it could, in theory, give it up. And what's something called that gives up an H? That's called an acid. So whatever the base becomes is the conjugate acid, and whatever the acid becomes is the conjugate base. Now, one last thing to touch on here is this idea of this H3O plus ion. This H3O plus ion is called hydronium. And in all the calculations we're going to do, hydronium is interchangeable with just simply H plus. The reason for that is if you think about a water molecule, here's a water. If you have a proton floating around in solution, it's going to latch on to this water here, forming this H3O plus ion, this hydronium ion. Since you can't have protons by themselves, they attach to water. For every proton that attaches to water, you get one hydronium. So for all intents and purposes, they're interchangeable in everything we're going to do. So let's try this equation down here in the blue. Find NH3 and see what it becomes on the other side. And it actually becomes this NH4 1+ ion. So what that means is this NH3 gained a hydrogen, so it must be acting as the base. And whatever the base becomes is your conjugate acid. And that means the H2O in this case must be acting as the acid, and whatever it becomes is the conjugate base. Just to check and make sure we're right, this water acting as an acid should have given up an H, and sure enough, it did. Now you might notice in this scenario, between the red and blue equations, in the red equation, water acted as the base. In the blue one, water acts as an acid. That's called, water is amphoteric, which means it can act as either an acid or a base, just depending on what's going on around it. Now, one last thing to point out about this is the fact that the stronger an acid is, the weaker its conjugate will be. And that's also true for bases. The stronger the base, the weaker its conjugate will be. And that even works in the other direction. If you have a really, really weak acid, it's going to have a strong conjugate. And one more thing, in an equilibrium mixture, equilibrium favors the weaker acid. So what this means is if you mix two weak acids together, equilibrium is going to push itself to favor the even weaker acid. The same is true for bases. If you mix two weak bases together, equilibrium is going to favor the weaker one. And we'll talk more about that in future lessons. So that brings us to the idea of a strong acid and a strong base. So all you need to know about strong acids and strong bases is that they fully dissociate. In an acid, every single one of those H plus ions is going to detach. And in a strong base, every single one of those OH minus ions is going to detach. So, luckily, there aren't very many of them. There are only 6 strong acids. They are HCl, HBr, HI. So you might remember these first 3, that they just kind of go down the halogens, chlorine, bromine, and iodine. Then the other 3 are nitric, which is HNO3, sulfuric, which is H2SO4, and perchloric, which is HClO4. These are what, and as far as AP chemistry is concerned, these are the 6 strong acids. Now, strong bases are your group 1 and 2 metal hydroxides. So what that means is any metal from group 1 or 2 combined with OH is going to be a strong base. For example, sodium's in group 1, so if you combine that with an OH, that'd be sodium hydroxide, which is a strong base. Calcium is a group 2 metal. Now it has a 2 plus charge, so it will take 2 1 minuses to cancel that out. But nonetheless, it's a group 2 metal hydroxide. So we're going to, as far as AP chemistry is concerned, assume that calcium hydroxide is a strong base. Now, why those are important is because everything else is considered to be weak. If it's not one of these 6 acids or a group 1 or 2 metal hydroxide, it is not a strong acid nor a strong base. It is a weak acid or a weak base. The most important part of that is that you understand they do not fully dissociate. They're only going to partially ionize, and instead they're going to establish some sort of equilibrium. So let's say we have an acid, just a random acid, HA. H for the proton, A for anion. I don't know nor care what that anion is. But let's say that that's dissolved, and it reacts with some liquid water. Since this isn't a strong acid, it's not going to have a one-way arrow as we would expect. It's actually going to establish an equilibrium where some and only a little bit of this H plus dissociates, releasing that hydrogen, which then attaches to the water, forming just a little bit of H3O plus, a little bit of that hydronium ion, plus just a little bit of that anion that's left over from the HA acid that we're not sure what it is. So strong acids and bases fully dissociate, whereas weak acids and bases only partially dissociate and establish an equilibrium instead.